Okay, so I've got a bullet slamming into this kind of offset pendulum with a couple of concentrated masses on it. It enlarges. I want to figure out what the angular velocity is after that impact goes on here. So for this, obviously there's going to be an impulse, right, of, this guy smashing into here, but if I take the two systems together, I can get the impulse internal to the system. That's how I can get rid of that one, okay? What I can't necessarily get rid of is these impulses here, right? Because when that bullet slams into that, there's going to be an impulse at the pin joint there, okay? And that cannot be neglected. Now, there are gravities, right? Those can be neglected because they're much smaller than the impulses that I'm talking about of the bullet slamming into that, and then whatever impulse that I have at the pin joint there. But we call gravity a non-impulsive force because it's so much smaller it can be neglected on this situation. Okay. So, but what I can't ignore is those points, those reaction points at point O, unless I do the momentum about that point O. And if I do the momentum about that point O, the only impulse that I potentially have is the impulse of them slamming together, which I can get rid of by taking the two together. So what I have here is the sum of the RMV1s, basically, I'll say about point O equals the sum of the RMV2s about point O. So angular momentum is conserved about point O because for the entire system. The entire system gets rid of the impulse between them, and then doing about point O gets rid of the impulse at point O. Okay, so from that we can just go ahead and start writing this. So my initial, okay, keep in mind that there's an initial angular velocity of the two as well as the velocity of the bullet. So let's start with the bullet. Okay, it's going to impact at an R of 0.4. Okay, it has a mass of 0.5 or 0.05, excuse me. And then its velocity is going to be 300, and again, I need that perpendicular velocity for that to find the, R cross MV. So I just need that, I've got a vertical R, I need the horizontal V, and I get 300 cosine of 20. Okay, and that's going to be creating a counterclockwise positive momentum. Now, this thing has a negative momentum initially, so it's swinging in the opposite direction. So that lower mass is going to be negative R 0.4, M 3.2, and then V. Remember that V is equal to R theta dot, right? R is fixed, doesn't change with time, so it's basically the arc length time derivative, right, which is R theta dot, okay? And again, theta dot is 6 radians per second, so I take that times 0.4 times 6. Now I've got the other one, everything's the same except it's only 0.2 meters away, okay? Same mass, and then 0.2 times that theta dot of 6. And again, those are negative, so the bullet is coming in with a positive angular velocity, RMV. Those spheres have a negative. And then again, that's going to equal my final angular momentum. Now, the bullet's lodged in the block, okay? It's RMV, it's 0.4. And again, I'm just going to assume positive. If I'm wrong, I get a negative answer, okay? It's going to be 0.4 times, so that's R, then M is 3.25 because now it is both the ball and the bullet combined, okay? And then times R theta dot, where R is 0.4, and then theta dot is what I'm trying to find, that final theta dot. Maybe I call that theta dot 2, okay? Then I've got the other one, everything's the same except it's 0.2 away on this one. So both 0.4s become 0.2, and then theta dot. So I've got this big equation. The only unknown that I have in it is theta dot 2, which is going to be 2.77 radians per second. So again, with this idea, take the two together, make that impulse internal to the system, and then recognizing that I've got an impulse at the pin joint, but if I take the angular momentum about that point, then that creates no angular impulse because it goes right through that point. So I have conservation of angular momentum about 0.0 for this system, for the entire system.